I think we can begin. Good afternoon to everyone. I'm Mario. I'm a postdoc at Nils Ture Group, and I will continue where he left. In previous lectures, you were having a look to some basic tools for working with deep learning with physics, and you also had a look to differentiable physics. Now we are going to have a look to some architectures that we can use. Specifically, we'll have a look to graph neural networks and how they can be used for working with particle and mesh-based simulations. As you can see from the diagrams I have included in this first slide, these graph neural networks are quite useful for applications related with computer graphics, like in this top image, and also is quite common in surrogate solvers for engineering, for instance, for structural dynamics or for computational fluid dynamics. So let's begin by answering what's a graph neural network. So basically, in simple terms, is a neural network applied to graph structured data. Now this poses another question: what's a graph? You may be familiar with graphs from data structure courses before, so this basically consists of a set of nodes and a set of edges. We can use the nodes to represent entities like particles, atoms, planets, and we use the edges to represent the relationships or interactions between them. And these are quite useful for modeling some physical problems. For instance, or specifically, we have systems consisting of n particles, discrete systems, like the n-body problem, where we have some bodies that are exerting some gravitational force between each other. We could represent this problem using nodes that represent the planets, and they have assigned attributes or features like the mass or their velocity or their position. And we can also have edges connecting each planet or each body with every other body. And those edges are representing the gravitational attraction that we have. Other case where graphs are quite useful are for representing molecules. We can use nodes to represent the atoms, and we can use the edges to represent the links or connections that we have within the molecule. And indeed, it was from the field of chemistry where the concept of graphs was first introduced many years ago. And once we have this graph representation, then we can process it using a graph neural network. But these systems, these examples here are discrete, and most of the systems we work with in physics, like fluids or deformable bodies, they are continuous. So it doesn't seem apparent that we can create a graph for them. But actually, when we work with numerical solvers for simulating fluids or structural dynamics, we first discretize our system into a set of nodes where we discretize them using meshes, and these meshes have nodes and edges. So using a graph representation can also be useful. There are different kinds of discretizations that we can use. So first we could use a structural discretization like a Cartesian grid. This corresponds, for instance, to this example on the left, where we have square or rectangular cells that are discretized in the domain. And if we have this kind of representation, then this is quite similar to having an image, and we could process it using a convolutional neural network or CNN. But other kind of meshes don't follow this structure. For instance, we can have an unstructured mesh like the one we have here, where each node can have a different number of neighbors. In some areas we have a few nodes, and in other areas we have a lot of nodes. So if we have this kind of unstructured discretization, then we could use a graph to represent our mesh and then process the information, for instance, in a surrogate solver using a graph neural network. These GNNs and graph representations also can be useful for Lagrangian discretizations. Maybe you're not familiar with this, but these Lagrangian discretizations discretize in the case of fluids, discretize the fluid into some moving fluid particles. So now these nodes or fluid particles are not fixed, they are moving with time, and apparently we don't have edges. We will need to create edges at each time step, but connecting each node to its closest nodes. And once we have that graph, we could process it using a graph neural network. Now, Why should we care about using a structure mesh if we have to use a graph neural network, which we don't know yet how to use it? We could just use this kind of regular grid and use a CNN. In some problems, it's quite useful to use a mesh or a graph representation because we may have complex geometries like this waving flag that, for instance, could be used to represent clothes in video games. And with this kind of graph representation, we can place the nodes on the surface of it. Also, if we have aerodynamic problems, we are representing here accurately the airfoil because we are placing the nodes on the surface of it, but also we can adapt the resolution over space. So here, far from the airfoil, we have a small amount of nodes because there's not much going on. The spatial gradients are quite smooth, and close to the airfoil, we can place a higher amount of nodes. For instance, here we have a comparison of what we have with a regular grid or Cartesian grid and what we have with an unstructured mesh. We see that we are representing this much more accurately, whereas overall here we have a fewer amount of nodes, believe it or not, compared to this other Cartesian grid. So this graph representation is much more efficient. Then the Lagrangian discretization is quite useful for computer graphics application. In engineering it's not that common, but it's also sometimes used if we have moving parts. For instance, if we have an engine and we want to simulate some liquid inside, or if we have different substances with an interface between them. For instance, if we have a gas and a liquid moving inside a deposit. In this case, using an unstructured mesh would be more complex, and Lagrangian simulations could be seen, and hence using a graph and a GNN as a surrogate solver is a possibility. In this lecture and the next two lectures, we are going to be focusing in detail into graph neural networks and how to use them for these mesh-based and particle-based problems. Today we'll begin by having a look into some definitions and classifications, and then we will see how graph convolution works and message passing, which is the most popular kind of graph convolution for physics applications. So in most machine learning tasks so far, for instance, in the exercises that you have been doing before, we are working with data that is given in the Euclidean space. This means that we can represent or store the data using tensors. For instance, if we have an image, we will have a three-dimensional tensor with one dimension for the width, another dimension for the height, and another dimension for the color channel. If we have a text and we want to process it using natural language processing tools, then we can store this using a two-dimensional tensor. One dimension will correspond to the sequence length, and the other dimension will correspond to the embedding for each of the tokens that we have. And this kind of tensor representation is very useful because if we have multiple samples, we can stack them across a batch dimension, for instance, and it's very efficient to train these models and evaluate models on this data on a GPU. Also, in Euclidean space, we can compute the distance between two data points using this. For instance, the distance between this corner and this corner can be computed by evaluating this formula. But when we may have data that is not given in the Euclidean space, is instead given in the form of a graph. For instance, in a citation network or in a social network, we can have multiple people that have different kind of connections between them. In this case, we cannot say that the distance between person A and person B can be computed according to this distance, for instance. Also, we cannot store the data directly as a tensor, and if we have different social networks, different samples, we cannot stack them across a batch dimension for efficient processing in a GPU. So we will see how to do this using graphs and graph neural networks. Other examples are traffic networks and molecules, and of course we have seen before that graphs are useful when working with physical problems. Okay, so here we have the formal definition of graph. So a graph consists of two sets. First we have a set of nodes, which we will assume to be finite, and then we have a set of edges, which we also be assumed to be finite. Each of the edges is represented as a tuple of nodes. For instance, here we have an edge consisted of the end nodes I and j. Depending if the graph is directed or undirected, this edge will have a fixed order or not. So if it's a directed graph, the edge ij is not the same as the edge ji, and if it's an undirected graph, it doesn't matter the order with which we represent them here. We have an example here of a directed graph, and we have here the notation for the set of nodes and for the set of edges. So let's have a look to some different classifications that will be useful later. So first, as I mentioned, we can have undirected graph where the edges don't have a direction and represent a two-way relationship. For instance, this could be a social network like Facebook, where if node I is friend of node j, then node j is also friend of node I. And in a directed graph, the direction actually matters. And they represent a one-way relationship. For instance, if we are talking about Instagram, if node I is following node j, it doesn't mean that node j is also following node I. Other definitions are multigraph versus simple graph. So in a multigraph, we are allowing for multiple edges, for repeated edges. For instance, here we have the edge 2, 1, 4 times. And when we store these edges into a list, we need to take into account the order with which we are storing them. Otherwise, we can confuse them. And in a simple graph, we're not allowed for multiple edges. We will be working with simple graphs, so we will not be allowing repeated edges. We will also be working with homogeneous graph, where there is only one kind of node and one kind of edges. Graph neural networks also can be applied to heterogeneous graphs. In these heterogeneous graphs, there are different kind of nodes and different kind of edges. For instance, in an e-commerce network, we can have a node for the user, a node for the product, and a node for the review. The reason these nodes are different is because each of them can have different features or attributes assigned to them. For instance, for the user, we can have the location, the city where they live, and the age, and for the product, we can have the price or the number of stars it has. So we have different kind of attributes, so we need different kind of edges. Sorry, different kind of nodes. And the same happen with the edges. We can have an edge for the user product and other kind of edge for the user reviewer and so on. A pseudograph is a graph where we allow self-loops. Normally in the framework that we are using, it doesn't matter if you're working with a graph or a pseudograph. And a self-loop, by the way, is an edge that goes from one node to itself. So it would be in this case the edge 1, 1. Hypergraphs can also be seen in some special cases, some special applications. For instance, here these hypergraphs they are a generalization of graphs where the edges can consist of multiple nodes, not just two, for instance. This edge consists of nodes 1, 2, and 4. And an important definition that I will be referring often is complete graph or fully connected graph. So if we have a graph where each node is connected to every other node, we say that's a complete graph, and the number of nodes that we have the number of edges that we have is equal to the number of nodes to a square. So the square of the number of nodes if we are allowing for self loops. And this kind of representation is quite expensive. If this applying a graph neural network to a complete graph is very expensive because we have complexity that scales quadratically with the number of nodes. So instead, we will be often working with sparse graphs. So we say a graph is sparse if the number of edges is, I think I should get the mouse. we say a graph is sparse if the number of edges is much smaller than the square of the number of nodes. So we will often be working with this to reduce computational cost. Okay, and another important concept is disconnected graph. So a two graphs, well, a graph is disconnected if it consists of multiple subgraphs between which there is no path. For instance, here this graph consists of 4 disconnected subgraphs. We have here 1, 2, 3, and 4. And we actually use this when training neural networks. So if we have, as I mentioned before, if we are working with a CNN and images, if we want to train, then we don't train for one single image. We stack several of those images across the batch dimension. Now we have 4 graphs like in this case, and we want to create a batch with these 4 graphs for training. We cannot stack them along any dimension because this graph has 9 nodes, whereas this one has 2, for instance. So what we do instead is join these independent graphs into a single one. For that, we just have to change the indexing that we are using. For instance, if this will be the first graph in the batch, well, let's use a 1. If this will be the first batch in the graph and this is the second one, and this was the first node in the graph, after joining them into a single graph, we will need this index 1 to be number 10. And the same, this will be node number 11 instead of being number 2. So this edge also, we will need to be careful to change it from be in the edge 1, 2 to be in the edge 10, 11. But after applying those changes, we can work with this graph without having any problem because there's not going to be interaction between them because there's not any edge between them. So this is a trick that we use for training in parallel with several graphs. Is everything clear so far? Okay, so now we'll have a look to some concepts related with adjacency. First, we will begin by considering undirected graphs. So the first concept is the node adjacent of a node. So we say that node 1 is adjacent to node 5 because there is an edge connecting them. Other adjacent nodes of node 5 are 2 or 4. And we say that all the adjacent nodes of a node form the neighborhood. So the neighborhood of node 5 consists of nodes 1, 2, and 4. The degree of a node, in this case the degree of node 5, corresponds to the number of nodes in the neighborhood or the size of the neighborhood. Because in the neighborhood we have 3 nodes, then the degree of node 5 is equal to 3. And now another definition is the distance between 2 nodes. So let's say we want to determine the distance between nodes 3 and 5. So for that we need to find the shortest path connecting both edges. So in this case we have this path and we also have this other path. Both paths here have a length of 2. They have 2 edges in between, so we say that the distance between nodes 5 and 3 is 2 hops, and we use this term hops, which is equivalent to the number of edges that we have to traverse. The adjacency matrix is used to represent the connectivity of the graph, and it's a square matrix where the element ij is indicating if there is an edge. The element in the row I and in the column j is indicating if there is an edge between nodes I and j. For instance, here for the second row and the third column, we see there is a 1. So that means that we have an edge, which is this one, between nodes 2 and 3. If we check here the third row and second column, we notice there is also 1 which corresponds to the same edge, so that is why this adjacency matrix is symmetric when we are working with undirected graphs. This is an unweighted adjacency matrix where the elements are 1 if there is an edge and 0 if we don't have any edge. We can also have a weighted adjacency matrix where the edges can be indicating other information. For instance, if this was a social network like Facebook, we can have a weight indicating for how long they have been friends, so for how long 2 and 3 have been friends. So that will correspond to this weight here. And in the case that we don't have an edge, we can use a 0 in the adjacency matrix, or a plus or minus infinity, depending on the problem that we are working with. And now let's consider directed graphs. So the definitions are the same as before. We just need to take into account if we are in the outgoing direction or in the incoming direction. For instance, 4 has as incoming adjacent nodes 1 and 3, but it doesn't have any outgoing edge. We see there is no edge going out. It doesn't have any outgoing adjacent nodes, whereas node 0 has 2 outgoing adjacent nodes. This also allows us to define the outgoing neighborhood and incoming neighborhood. The incoming neighborhood of node 4 consists of nodes 1 and 3, and we have also the in degree and out degree definition. So the in degree of node 4 is 1 and 3 because it has the in degree is 2 because it has 2 incoming nodes. The out degree is equal to 0 because it has no outgoing edges. For node 0 is the opposite. The out degree is 2 and the in degree is equal to 0. And in this case, the adjacency matrix is not symmetric, and it's indicating, well, the row I is the element in the position at row I and column J. It's indicating if we have an edge going from I to J. But in this case, as you can see, if we check the row J and column I, now we don't have a 1 as before. Here, if you compute the sum across the rows, you obtain the out degree of a node. So here you will see that the out degree of node 0 is equal to 2. And if you compute the summation along the column, you obtain the in degree. So the in degree of node 4 here you can see is 2. So this adjacency matrix representation of the graph is very useful because it allows, for instance, to compute the in degree and out degree of a node very efficiently, which is an operation that sometimes we need to do when we are doing message passing. It also allows to compute aggregation operations easily. The aggregation is another operation that we will see later. But let's say for each node we have an attribute which is indicating the amount of or the age of one person. Let's say this is indicating the age of a person with 40 years. The age of person 1 is 31. So we can place those features into a vector. For node 0 we had 10. For node 1, it was a 40. We had 40. For person 1 we have 31. And when we compute this multiplication with this matrix and this vector, what we obtain is the summation of the age of each person, of the neighbors of each person. So for node 4, we will obtain the summation of the ages of person 1 and person 3. So as you can see, this adjacency matrix is quite efficient for computing these things. However, we are using 25 elements and we are just storing 6 elements here. So in terms of memory, it's not efficient at all. That's why we go to other representations like the adjacency list and the edge list, which is what we will be using. So this list contains all the edges in the graph. So as we can see, we have here edge 01, the edge 02, and we are placing the edges as tuples, and then we just create a list with these tuples. This representation, however, is not that efficient. For instance, if we want to find the neighbors of a node, if we want to find the neighbors of node 4, we will need to go through the whole edge list. So the time complexity scales linearly with the number of edges, whereas with the previous representation with the adjacency matrix, if we want to check the number of neighbors of node 4, we just have to check its corresponding row of columns, so the time complexity is equal to 1. In order to mitigate that, some software working with graph neural networks creates some special ordering for storing the edges. So you can see that here we are storing the edges in increasing order of the index of the second node. We call the first node in a directed graph as the sender node, and we call the second node as a receiver node. Terms that come from message passing, as we will see later. So here we are storing the edges in increasing order of the receiver node. And this way is a bit faster if we want to find the neighbors of a certain node. Okay, so now we have defined what's a graph and how we can represent its connectivity. Now we can see what inputs we provide to a graph neural network. So first we have the adjacency matrix itself, or the edge list. Normally if we are doing message passing, we use the edge list. If we are working with spectral graph convolutions, we use the adjacency matrix. And each of the nodes can have some attributes assigned to them. For instance, if we have one of those CFD meshes for discretizing a flow, at each node we can have the different components of the velocity vector and also the pressure vector. So with this vector for each of the nodes, we can create a matrix that we call the node feature matrix. So this is a matrix where the number of rows is equal to the number of edges, to the number of nodes, and the number of columns is equal to the number of features that we have. So if we have horizontal and vertical components of velocity and the pressure, then we have three columns here. For the edges, we have something similar. So we were using an edge list representation. We have some features for each of these edges also stored in the order in which we are storing the edges in our edge list. So we can have in the end a matrix where the number of rows is equal to the number of edges. This will be the first edge, the second edge, and so on. And the number of columns is equal to the number of features that we have for the edges. For instance, if we have an edge connecting two nodes, we can have the relative position or the vector connecting those two nodes. So if we are in 2D, then we have two columns here. Okay, so here I have one example of how we represent this information for working with a graph neural network. We consider first this case where we have a particle-based simulation. We have our fluid discretized into some moving fluid particles, and the nodes of our graph are going to be equal to the nodes that we have in this Lagrangian simulation. By the way, this kind of simulation is normally we use SPH simulations for this, which stands for smooth particle hydrodynamics. I may mention that term later, so just for you not to be confused. And we need to create, we don't have any edges, so we need to create them. At each time step, we create them following different strategies. One strategy could be to create a sphere with a radius r, which will be a hyperparameter of the model, and we connect this central node with every other node. So we will have a directed edge going from the neighboring node to this central node. Another strategy is, instead of using this sphere, we can directly create, we can use the k-nearest neighbors algorithm to create an edge going to each node from its k nearest neighbors. So, okay, so now we have the nodes and we also have the edges. Now we can assign them features. Some possible features that we could have for the nodes is their spatial location. is their spatial location, also their velocity, the acceleration due to gravity, any external force, the distance to the wall of the particle, and also some mask that we could use to indicate if we have different kind of substances. If we have two substances, we can have the value in the mask equal to 1 if the node belongs to substance 1, and the mask equal to 0 if the node belongs to substance number 2. These are just possible input features. I'm not saying that this is the best selection. We'll see later that we don't want to have the absolute coordinates of the node. And then on the edges that we created later, normally the input features that we use are the relative position between them. So it's a vector going from the sender node to the receiver node. And we can also have the distance, the absolute value or the magnitude of this vector, but that's not needed. That information is already here. Okay, and if we are working with a mesh-based simulation, we already have our mesh from CFD. Normally we don't directly use meshes used for numerical simulations because these are very fine, have lots of nodes, and the advantage of using a deep learning surrogate is that we can use a coarser mesh, so it's going to be faster. But anyway, we have a mesh generated by some mesh generator software, and we can directly use the nodes and the edges provided by that mesh. We could also create new edges, so we preserve the nodes that we have before and we create new edges using the k-nearest neighbor algorithm or using a sphere or radius r as before, and that's not that important. And then, as before, we assign features to the nodes. Well, by the way, normally we use B for denoting the node features, and we use an E for denoting the edge features. So features or attributes that we could have for each node are the Eulerian magnitudes that we want to predict, like the velocity and the pressure. We can also have external force, the distance to a wall, and a mask for indicating if the node belongs to different parts. Like we can have a mask for indicating if the node belongs to the wall or to indicate if it belongs to the inlet, and so on. Okay, so now we can have a look to different kinds of graph convolutions. So when there are two kinds of graph convolution. We will see first the spectral graph convolution and the spatial graph convolution. Both are considered generalizations of the convolutions in CNNs when we are working with images or Cartesian grids. However, we cannot use directly these convolutions, the discrete convolutions that we have in CNNs, because we don't have, for each node, we cannot say that we have a node up or a node down or a node right. For instance, if we are in a citation network or in a social network, it doesn't make sense saying that person A is on the top of person B. And if we have a mesh like this one, then also we don't have a node, we have a node on the top of node A, let's say, but it's not just on the top, it's on the top, but maybe to the right or to the left some amount, and it's not on a discrete distance, but a continuous distance. So we need to take those things into account. And these two attempts that try to generalize convolutions, the discrete convolutions applying CNNs to unstructured data, follow different ways or interpretations of convolution. So with the spectral graph convolution, we are considering convolutions from the mathematical viewpoint. So the idea here is take our graph, apply some transformation, which is equivalent to a Fourier transformation, and in this Fourier space we can convolve with our filter by doing an element-wise multiplication, and then we go back to the physical space or the graph space. And in the spatial graph convolution, we are leveraging the idea that in a convolution, each node is sending a message to the central node. So yeah, we will have a look in detail to this. So let's begin with these spectral graph convolutions. First important thing is that they only work with undirected graphs. They don't work with directed graphs. And they come or borrow ideas from graph signal processing. And here we work with signals, so we need to define this, but actually there's not much problem. So if you remember before, we had our feature matrix where the number of rows is equal to the number of nodes in the graph, and here we have different features like velocity along x, velocity along y, and pressure. So a signal corresponds to just taking one of these columns. So we are going to be applying convolutions independently to each of the columns first. Okay, so we have our graph signal, and to apply this spectral graph convolution, we need to take it to a graph Fourier transform. It's not really equivalent to the Fourier transformation, but some ideas still hold, like we can apply convolutions as an element-wise multiplication. So I guess that's why we call it graph Fourier transform, although it's not strictly a Fourier transform. So for computing these graph Fourier transformations, first we need the adjacency matrix, and we compute the Laplacian matrix, which is obtained by subtracting the adjacency matrix to the degree matrix. This degree matrix is just a diagonal matrix that contains the degree of each node in the diagonal. We can compute it by this, doing the summation over the rows or over the columns of our adjacency matrix. In reality, we don't work with this Laplacian matrix. We work with the normalized version of the graph Laplacian, because we know that the eigenvalues are between 0 and 2, and it will be more stable when doing the eigenvalue decomposition. And that's the second step, computing the eigenvalue decomposition of this normalized graph Laplacian. Here lambda is a diagonal matrix where in each of the rows, each of the elements corresponds to an eigenvalue stored by decreasing order, and U is the matrix of eigenvectors. So each of the columns corresponds to one eigenvector. Okay, so now that these matrices are normalized, each of the eigenvectors has been normalized to be unitary. Yes? Mm-hmm. Around 100 nodes. We'll see that's one of the problems, because the eigenvalue decomposition scales cubically with the number of nodes. So if we have thousands of nodes, it becomes very expensive. Okay, so now that we have computed this eigenvector matrix, the graph Fourier transform is done simply by multiplying the transpose of the matrix with our graph signal. This corresponds to projecting our graph signal along each of the eigenvectors. Remember, here we had in the columns the eigenvectors, which the transpose they are in the rows, and we just do the multiplication. It's like projecting our graph signal into another system of coordinates. And if we want to compute the inverse, we just multiply it with the untranspose or no transpose matrix. And well, here the transpose of U is equal to the inverse of U, because this normalized Laplacian matrix is real and symmetric, and also the rows, the columns, the rows and the columns are normalized. So it's an orthonormal matrix, and we can compute the inverse just as the transpose. Okay, so now we know how to compute or how to express our graph signal in the graph Fourier space. So to apply a convolution to our graph signal with a filter with number of elements or weights equal to also the number of nodes, what we do is we apply the graph Fourier transform of the graph signal, the graph Fourier transform of the filter. We do the element-wise product because in the graph Fourier space convolution is equal to element-wise product. These are two vectors, so we are just multiplying each of the elements of the vector, and then we compute the inverse of the transformation. So we have it here replacing the transformations with the matrix U. Now here, since we are always going to be the convolution in the graph Fourier transform, we can use directly a filter that lives in this graph Fourier transform, so we don't need to, in this graph Fourier space, sorry, so we don't need to be doing this operation all the time. We are going to denote it as G theta, and we are storing actually as a diagonal matrix too, so this diagonal corresponds to this transformation. But we are not going to be working anymore with the filter in the graph space. We work directly with it in the graph Fourier space and given us this diagonal matrix. Now, because this is just element-wise product, we have the commutative property and we can bring this to the front. And because of the associative property, we can remove the brackets. So that's all we are doing when going from here to here. And this will be the expression that we will keep using for the spectral graph convolution, which looks a bit strange, but it's easy to remember. First we compute the graph Fourier transform, we do the convolution, and then we go back to the original system of coordinates. Any question? Okay, so let's continue. This idea taken from graph signal processing can be used directly to create a graph neural network. That was done in the spectral CNNs proposed by, well, the author is here, proposed by Bruna and collaborators. And they just directly use the definition that we had before, but since we can have multiple input features for each node, and we also may want multiple outputs, like when we work with CNNs, with each layer we have a number of input channels and a number of output channels. So they generalized that expression before by adding here this summation. So what we are doing is for each pair of inputs for each pair of input channel and output channel, we are applying that definition. So now instead of having just one G theta matrix, we have a, well, it's a bit strange if I write it there. We have that G theta matrix and a C in times C out times. Okay, well, they call it a spectral CNN also. This is a bit confusing. It's actually a GNN, but since it was one of the first graph neural networks, they still didn't started using that term. And in one of these GNNs, what we do is we have one of these spectral convolutions. Then we have an activation function, spectral convolution, activation function, and so on. Here there are several things to notice. So in normal CNNs, when we apply a convolution, each node is only seeing information from the very neighboring nodes, depends on the size of the filter. But here this convolution has a global receptive field. Each node is receiving information from every other node because we are doing the convolution in the graph Fourier space. Another thing to notice is the number of weights. So this is a question that could be asked in the exam, for instance, very easy question. If we have a spectral GNN with 10 layers, 10 of these spectral convolutions, how many weights do we have? So the answer would be the number of layers that we have times the number of input channels and output channels that we have in each of them, uh, times the number of weights that we have for each pair of input and output channels. So this was one of the weights of the weight matrices, and if you remember, this matrix was the matrix G theta from before, which was this diagonal matrix where we have only the elements that are non-zero. This is the number of nodes. So the number of weights that we have in the network is this, assuming that every layer has the same number of input and output channels. Okay, so that's all regarding this first implementation of the spectral graph convolution. Now, there are some problems that we have. So, as your colleague pointed out later, the time complexity of the eigenvalue decomposition scales with the cube of the number of nodes, so we have a very large graph. This stops working. Also, in our expression here, we have the we have the eigenvector matrix, which means that when we train our model, we train it specifically to work with this matrix. If we have a different graph where the adjacency matrix is different and hence the eigenvectors are also different, this is not going to work anymore. We will need to train a different network. Well, also, if we have a larger graph, then the size of the kernel will have to be different. This diagonal will be longer. So it's slow and it's also not generalizable. It still can be applicable to some cases, like for instance, well, in the case of weather prediction, we have too many nodes, but the graph structure is still fixed. But for instance, in finance networks, where let's say each node represents some stock and the edge represents the bid or offer price for them, these graphs are always going to be fixed, and we don't have that many nodes, so still we could use this spectral CNN. However, for our purposes, we are going to be considering other cases that are going to, instead of having a global receptive field, we are going to have a local receptive field. Each node can only know what's happening around some neighboring nodes for each layer, but in turn, the time complexity is going to be smaller, scaling linearly with the number of edges instead. And before having a look to that, we can have a break. Well, any question before? Okay. Okay, let's continue. So we saw before those problems with the spectral CNNs. They don't work with the different connectivities for the graph, and also they are quite expensive to apply because we need to compute this the eigenvalue decomposition. But well, I should mention this eigenvalue decomposition only has to be computed once. It doesn't have to be computed for every layer, and each time we evaluate the network, we can compute it once before training, and then it will remain fixed. But still, it's quite expensive. It will have thousands or tens of thousands of nodes. It can even become unfeasible for stability reasons to have all the eigenvalues and the eigenvectors. So let's see the Chebyshev spectral CNN, which applies a series of assumptions and simplifications to that original definition of spectral CNN. So we are going to be looking just to what happens to each pair of input and output channels. Then we will need to repeat this for every pair of input and output channels, and we will have this summation across them like before. But for simplicity, let's just look into that. So before we arrive to this expression for the filter in the graph Fourier space, and it was a diagonal matrix with a number of elements equal to the number of nodes. Now we can express that square matrix as a summation of other diagonal matrices. These diagonal matrices correspond to the Chebyshev polynomial evaluated with input the normalized eigenvalue matrix. So we will have here the Chebyshev polynomial of order 0, which is just equal to the identity matrix plus another parameter multiplied with the Chebyshev polynomial of order 1, which is just equal to x. So this will be equal to the normalized eigenvalue, and the rest of the Chebyshev polynomials are computed iteratively according to this. This expansion we truncate it up to order k. Is this more or less clear? I think it's simple. So we are just rewriting our filter as an expansion of Chebyshev polynomials. And now the learnable weights are not the elements of the diagonal matrix. This matrix is fixed. It depends of the adjacency of our matrix. And the learnable parameters are going to be these weights or coefficients of the expansion. We are using the normalized eigenvalue matrix, which corresponds to taking the eigenvalue matrix we had before and multiplied by 2, divided by the maximum eigenvalue, and subtract the identity matrix. That's because with this normalization, the eigenvalues are between -1 and 1. Remember that for the eigenvalue matrix, the eigenvalues were between 0 and 2, so after normalizing it like this, they are between -1 and 1. And this is for stability reasons when doing these recursive multiplications. Okay, so if we replace that filter into the expression we have for the graph convolution, we have something like this. The reason we were using Chebyshev polynomials is that the composition of what we have inside is equal to the composition, the eigenvalue decomposition of the polynomial. So that means that we can take these matrices inside the brackets, and we have here the normalized Laplacian. We have it with these numbers around here because of this normalization that we did before. And in reality, we are just placing it inside, and we recover the adjacency matrix. And that's all. Another simplification that we do is assuming that the maximum eigenvalue is equal to 2, which I mean is not a very strong assumption. It's quite common. So if you notice with this expression, once we have removed here the maximum eigenvalue, we don't need to compute the eigenvalue decomposition of the Laplacian matrix. So now anymore we don't have that time complexity scaling with the cube of the number of nodes. Instead, now the time complexity scales linearly with the number of edges, because the only thing that we have is multiplying this matrix with with this vector, and that's express matrix multiplication. And well, here we are multiplying with k, but normally k is a small value, which is the number of elements in the expansion of our weight. And I will not show that, but this k value also corresponds to the size of the receptive field. So if k is equal to 1, then each node is getting information from its direct neighbors, from its neighborhood. If k is equal to 2, then it's getting information from its neighbors and also from the neighbors of its neighbors. So the larger is k, the larger is the receptive field. So now we don't have any more, after truncating our filter like this, we don't have any more a global receptive field. It's a local receptive field. But that also has the advantage that this can work with different kind of graphs, because we are not considering the graph as a whole, we are just considering it locally. We can train it for different kind of graphs, and it will still work at inference. Now we have, well, the number of weights that we have here after we consider the different number of input and output channels will be the number of input channels times the number of output channels multiplied with the number of weights that we have in the layer. So that's equal to k, the order of the expansion. Okay, now this graph convolution network is another simplification to the Chebyshev spectral CNN, and it's quite common if you read some papers, not about deep learning for physics, but more about citation networks, or even for weather prediction, or some first papers considering GNNs for physics. You will see they use this kind of graph convolution. So what they do is they consider the Chebyshev CNN with a k equal to 1. They have the same assumption as before, that the maximum eigenvalue is equal to 2. And they also say that the only two weights that we have, because k is equal to 1, are equal but with different sign. So if you do those simplifications here, you arrive simply to this, where we have only a weight, because we assume they are equal but with opposite sign. Also in this paper, they found that it's better to add a self loop to every node. So with each of these layers, the node is not getting only information from its neighbors, also information from itself, which makes sense. So after doing that, well, we add self loops by adding to the adjacency matrix the identity matrix. So we have a modified adjacency matrix and also a modified degree matrix. So if we take those considerations into account, then we will be rewriting this bit as this. Where here we are just modifying this definition for the Laplacian matrix. Okay, and now we have multiple input and output channels. Then we can write this. Well, here we only have one weight. Yeah, as I was saying, if we have multiple input and output channels, then we can rewrite it like this, where this is our whole feature matrix. So it has V number of rows and Cn number of columns, and our kernel or filter has a number of elements equal to the number of input channels times the number of output channels. So this is quite similar to what we have in the discrete convolutions in CNNs, but we are adding this normalization term. Okay, and this graph convolution network can also be written using this other formula. Here BI represents one of the columns of our adjacency matrix. Sorry, one of the rows of the adjacency matrix. This is one of the nodes. So if we want to obtain the new feature vector for this central node J, what we do is for each of its neighboring nodes, we multiply them with our filter, with our weight transpose. Then we apply this normalization, which corresponds to this normalization with this normalization here. Then we compute the summation, so the summation for those results over all over the whole neighborhood, and then we compute the same for the central node. Is the same operation here and the same normalization, and we add that result. I'm saying this that looks a bit convoluted because this is what we know as message passing. So message passing is a general framework, and we can rewrite the graph convolution network, which comes from spectral graph convolutions, as one kind of message passing. Well, message passing is also known as the spatial convolution. And in this general framework of message passing, the first step corresponds to computing the message. So that's what we are doing here. For each of the nodes and edges, we compute the message, then we aggregate the result. In this case, the aggregation is the summation. And then we have a node update function, which is taking that aggregated value and adding it somehow to the features of the central node. Okay, so now we have finished with that family of convolutions, the spectral convolutions. Now let's have a look to the spatial based convolutions. So here the idea is similar to what we were doing in CNNs intuitively. So in CNNs, let's say we have a kernel size of 3 by 3. What we do is for each of the neighboring nodes, we multiply them with a weight, which is different for each of the neighbors. We do that with all of the neighbors and also with the central node, and add the result. So here we have that multiplication and this summation. We could do the same with a GraphNet. So for each of the nodes we have some feature, we multiply it with a weight for each of the edges, and we add it. So that's the general idea. But now we don't have, like, this was the W1 was the weight for the node located in the top left corner. Now, as I mentioned before, we cannot talk about top or left nodes because they may have no location in space, or the location can be continuous. So we need to define some more complex ways of computing these weights. Okay, so that's summarized here. So this weight that we were using to multiply the features of each node can be directly a learnable weight, which is the same for all the neighboring nodes. That's what we're doing before in the graph convolution network. We were multiplying all the neighboring nodes with that fixed weight. We have this fixed weight plus this normalization. Or what we could do is multiply the features with some learnable weight, but now we are not learning the weight directly. We are learning the parameters of a function that takes as input some features. Like this could take as input also the values of the node and of the sender node, all the features of the receiver node, and the features of the edge connected to them, which is what we have here. This feature could be, for instance, a vector indicating the relative position from the central node to the neighboring node. And this function could be, for instance, an MLP. So now the weights correspond to the weights of the MLP, and for each of the neighboring nodes, because they have a different location in space, this result is going to be different. I mentioned that this could be an MLP, but it could be any other parametrical function. For instance, in the spline convolution, they use as learnable weights the coefficients of a B-spline basis. And the most general way of doing it is forgetting about using weights and directly compute a message. So instead of computing this multiplication and then adding that, we are going to directly parameterize the message as a learnable function. For that function, we could use an MLP, for instance. So this MLP can take as input the edge features, the features of the sender node, and the features of the receiver node, concatenate them into a single vector, and then we apply the MLP. So with that, we obtain a message for each of the neighboring nodes, and then we add the result. So that would be one way. Besides computing messages, we also need to define how to update the features of the node. That's done with the node update function. And well, the node update functions can differ a lot, so I haven't established any classification as I have done for how to compute the message. We have here because these messages can be defined in many ways, and also the node update functions can be defined in many ways. Gilmer and colleagues came with the idea of establishing a general framework, so people stop saying that they invented a new GNN. We have a general framework, and everything can be explained with this general framework. So in message passing, we have 3 steps. First, we have the calculation of the message. So for each of the edges that we have in the network, we are going to compute in parallel a message by evaluating the edge update function, which is just some learnable function like an MLP that takes as input the features of the edge and the features of the sender node of this edge and the features of the receiver node of the edge. And well, this can be done quite efficiently since it's an MLP where we can use the batch dimension of the MLP for each of the edges. The most expensive part can be finding the sender node and the receiver node for each of the edges when we iterate through them. Then after we have computed the messages for each node, we are going to aggregate the messages of all of its neighbors. I have a diagram here. So after we computed messages for each of the nodes, we aggregate all of them for the central node J. That aggregation must be some permutation invariant function. Could be the maximum, the minimum, but what makes more sense and what we often use is the summation or the mean. Here I'm expressing the mean. This thing here is just representing the in degree of the graph. So this n symbol with a minus sign on top indicates the neighborhood of node J, and because we have the bars here, it denotes the size of the incoming neighborhood of node J, which in the terms that we introduced before is just the in degree of node J. And once we have computed this message, this aggregated message, so each node has some aggregated message, we need to use that aggregated message to update the features of the node. For that we have the node update function, which is any learnable function that takes as input that aggregated message. I was in this slide, so it's quite similar. So we have this aggregated message, and we also feed to this MLP the current values for the node features. Well, I said MLP, it can be any learnable function. Is it clear? Okay. So now that we have this message passing layer, we can apply them sequentially. So when we apply them sequentially, we are increasing the length of the network, we are increasing the level of abstraction, and we are also increasing the receptive field. So after one message passing step, this red node can see what's happening in its immediate neighbors. After 2 message passing steps, it can see what's happening also to the neighbors of its neighbors, and so on. And in physics, in continuous domains like fluid dynamics or structural dynamics, what's happening in a node can influence what's happening to a node located very far away. So we need many of these message passing layers to have a large receptive field. And between each of the message passing layers, we could have an activation function or not. When using message passing, it's not that common to have an activation function because we already have them here in the update function and the message function. These are already non-linear functions. Okay. And a further generalization to this idea of message passing was later introduced by Peter Battaglia and his colleagues at the DeepMind. So based on this algorithm that we had before, at each message passing layer we compute a message with we use to update the value of the node features, but the next time we apply a message passing layer, we will need to compute another message from zero using whatever edge features we have, like the relative position between the nodes. Instead, what Peter Battaglia was doing here is, after computing the message, use that message to update the value of the edges. So here we are using the value at the edge to update the value of the edge, then that's also used to update the value of the node. And the next time we evaluate a message passing layer, the edge features have been updated already and they are not the same as before. So this is another way of increasing the depth of the network, and the accuracy is also better. But as you may notice, it will be a bit more expensive to train because when we do the backpropagation, the backpropagation chain is going to be longer. We also have to backpropagate through the edges across the different message passing layers. Okay. Well, before I was talking in general about, well, I should mention that this is just simple notation, but if there is no edge update, we just refer to this function as the message function. If we are updating the edges to them, it's not just a message function, it's the edge update function. And here now we add the name node is the we add the name node is the node update function. And these are general learnable functions, but what we often use is an MLP. So we concatenate the edge and, well, the features of the edge and the features of the sender and receiver node into a single vector. We apply layer normalization, and then we apply the MLP, and then we have also a skip connection, a weighted skip connection. And for the node update function, we have the same. We concatenate the aggregated features and the node features into a single vector, apply layer normalization, MLP, and a weighted skip connection. Any questions? Okay. So now we can, well, we have finished with this, having a look to spatial graph convolutions or message passing and the spectral graph convolutions. In this table, I'm listing some of the differences that we should take into account. So spectral graph convolutions only work with undirected graphs. If we have a directed graph, then we will be using message passing. If we have an undirected graph, we can still use message passing, but we need to take it into account and be careful. So for each undirected edge, we will have now two directed edges. So the edge is transformed into a bidirected edge, and each of these edges must have the same input features. It will not make sense if they have different features. And if we are predicting things at an edge level at the end, because we will get a different output for each direction of the edge, we will have to compute the mean of them, so we get a single value for both edges. So we cannot apply directly message passing to undirected graphs, but being careful after some tricks is possible to do it. Then important difference also is that the spectral graph convolution only works with node features. We cannot have edge features as input or output, and whereas the spatial one can work with both. The message passing works with local information. At each step, each node is receiving information from its neighboring nodes. And with the spectral graph convolutions, in the initial formulation, we had a global receptive field, and then in later simplifications, we had also a local receptive field. And the same happens with the time complexity. If we have a local receptive field, the time complexity scales linearly with the number of edges. If we have a global receptive field and we need to compute the graph Fourier, we need to compute the eigenvalue decomposition, then we have a cubic time complexity. Now, for most of the applications we will see, we prefer to use message passing, mainly because we can have edge features. So by having edge features, we are going to assign to the edges the relative position between the nodes. And now we don't need to provide the absolute position of the nodes as another input. I think we will see that clearly when we see some examples. The advantage of not using absolute positions, using relative positions, is that if we shift our graph in space, the inputs are going to be the same. That means that the GNN is translation invariant, similar to convolutional neural networks, and one of the reasons of the success of these kind of networks. The Python geometric is probably the most popular library for working with graph neural networks. It's quite useful because it provides tools for creating graphs and for creating batches of graph by joining several disconnected subgraphs into a larger graph, as I explained before of the graph, and also provides implementation for the most popular spatial and spectral graph convolutions. So I think if you are interested, you can have a look to the examples they provide. Okay, so before continuing with some examples, here I have one schematic of what a standard graph neural network consists of. So we have several graph convolution blocks that are used to increase the depth of network, increase the level of abstraction, and if we have message passing, also to increase the size of the receptive field. Each of these blocks is taking as input node features. If we are working with message passing, then we also have as input edge features. And if we are using an edge update function instead of just updating the edges, these edge features that we have actually come from previous layers. So we also have depth along the edges. Here this encoder is used to increase the dimensionality, so this input vector can have only this feature vector at each node can have only a few number of elements or channels, like the horizontal and vertical components of the velocity and the pressure. So we use what we call encoder, which is just an MLP or a linear layer to increase the dimensionality of this vector. And the same for the edges. We can have only two components, one for the x relative position and another one for the y component, and we increase the dimensionality using an MLP or a linear layer. And at the end we have some features for the nodes and some features for the edges, which can be some high dimensional features, with f being 128 for instance. And to obtain the output that we really want, like the velocity and pressure at the next time step, we need to take into account which kind of prediction we are doing. We can have node level predictions, edge level predictions, or graph level predictions. So in the case of time stepping, what we want to have is a node level prediction. At each node we want to have the velocity and the pressure at the next time step. So here we will have a linear layer or MLP applied independently to each of the nodes. to reduce the dimensionality. So we are going to a vector with 3 components. We can also have edge-level predictions, which are not that common in physics, but for instance, in molecular graphs, they are quite common to indicate the probability of 2 atoms being connected, for instance. So in that case, we will not have the linear layer or MLP applied to the nodes. Instead, we will have it applied to the edges to go from a high dimensional vector to vector with the number of components that we need, depending on the problem. And in other cases, we may want a single vector or some features for the whole graph. For instance, if we are doing graph classification, or if we have some simulation and we want to infer some physical parameter like the Reynolds number, some global parameter. So in that case, there are several alternatives. We can flatten all the node features into a single vector and then apply an MLP to this flattened vector. This is not going to be permutation invariant because it depends of the ordering of the nodes here. So that's not ideal. Another option is to take the vectors that we have for each node and add them. And after they have been added, we apply an MLP. So in this case, this is permutation invariant because here we have the summation of aggregation. It's well, we have the commutative property. However, maybe this vector that we obtain at the end after this summation is not expressive enough, and we have a very large graph. The most common is using graph pooling, which is something that we will see not in the next lecture, but in the one after the next lecture. Okay, so now we are going to have a look to particle-based simulation. We will do this by going through some very important papers in this area. We are approaching to the end of the lecture, but I think I can go through the beginning of this first paper. So this first paper was published by Peter Battaglia again and his collaborators at DeepMind, and was the first paper applying graph neural networks to physical simulation. They applied to systems consisting of, well, to discrete systems with a finite number of elements. In this case, they have quite a small number of elements. The problems they consider is the n-body problem or gravitational problem, balls bouncing within a box, and also a spring interacting with a fixed ball. This spring was discretized into several nodes. And they apply as the graph neural network consisted of a single message passing layer. I will show later that with a single message passing layer we can describe quite accurately what's happening for instance in this gravitational problem. Whereas if we consider other architectures, like for instance, if we use an MLP for instance for this problem, one of the problems that we have is that we train our network to have 6 nodes. If we have then at inference time 7 nodes, the MLP will stop working because it has a fixed input size. Whereas if we have a graph neural network, then we can just have 1 node more in the graph, but it still will work. We could use, for instance, a CNN, which has been used before GNNs were used, and to this CNN we are providing directly the image. We are providing an image of the system, but we will need a deep CNN, maybe a unit that will have to learn to identify each of the particles and then how they interact with each other. Whereas using a GNN is a much better formulation where we have this inductive bias, where we are decomposing our problem into elements or nodes, and then we are modeling their interaction using the edges. So This is to demonstrate how powerful is message passing in this kind of problems, but let's forget about message passing first, and let's consider the M-body problem, where we have M bodies and each body has a gravitational force to each other body. Then, according to Newton's gravitational law, the acceleration that we have at each node, let's say at node I, is going to be the result of this summation here. And after we have computed this, well, this is the sum of forces, but we are dividing by the mass, so we have the acceleration. Once we have this acceleration, we can time integrate twice. That's what we are doing here, using Euler integration, and we obtain the location for the node or for the body and the next time step. So if we pay attention here, this thing that we did before could be a message function, no? Is taking as input the features of the receiver node, for instance, let's say, yeah, the features of the receiver node, for instance, its location, the features of the and its mass. Sorry, this is the sender node. The features of the sender node, like the mass and the location. Also the features of the receiver node, like its location, and some features for the edge, like the distance. This could also be a feature of the edge instead of being a feature of the nodes, and it's actually better. And after this message is computed, what we have is an aggregation here. And after that aggregation, we use this aggregation here together with features for the node to compute the node update. So we have obtained the position of the body at the next time point with a single message passing function. We don't need to have a CNN with multiple convolution layers, and this expression also is quite general. It fits quite well within the physics what's happening, whereas if we use an MLP, it's not going to generalize so well. So this is one of the reasons why message passing is so good, because we are working directly with nodes and edges. Okay, I think we can stop here, and the next day we'll continue from here. Do you have any question before? Okay, then thank you and see you next day.